Welcome back to the Cosmic Classroom. We'll now talk about the solar weather. The sun has weather just like the earth does, for different causes though. So the sun has a very strong magnetic field, and it's the magnetic field that causes the weather in the surface of the sun. There are different kinds of weather systems, and I'll summarize the three most important ones here. Okay, so here is a sketch of the sun with the north magnetic pole, with the north pole and north magnetic pole, and the sun is rotating. And in pink here you see the magnetic field lines. Now, as the sun rotates, it drags the magnetic field lines along with it. But the sun has a funny aspect to it, in that because it's this big ball of gas, it doesn't rotate with the same velocity everywhere. So as you can see here from the size of the arrows, the speed changes. The rotation near the equator is faster than the rotation near the poles. So when the sun starts spinning, it drags the magnetic field lines, and the magnetic field lines near the poles are left behind, and they get all entangled after a while. Okay, and eventually this entanglement just dies out, and the process starts all over again. But it is this differential rotation of the sun as a function of latitude and the magnetic field that causes the weather. Okay, so in here it's a zoom that shows the magnetic field lines, the direction of the magnetic field lines, and what happens to an electron in a magnetic field line. An electron will spiral in the magnetic field line. The reason why that's important is because a lot of the light that we see emitted is coming from those electrons that are being accelerated. The electrons are spiraling in the magnetic field lines, accelerating and emitting light. So that's why it's important to understand what are the electrons doing. Also, the kinetic energy of the electrons tells us about the temperature, right? The faster the particles are moving, the hotter the spot on the surface of the sun. So if we zoom in the surface of the sun, you'll see regions that we call sunspots. Sunspots are regions of cooler temperatures. So what you see here in dark are regions that are cooler than the average in the surface. So the surface is shown here in yellow, and you see the granulation if you look closely. This is because of convection in the surface of the sun. The heated gas is coming up in the surface of the sun, and you have these regions of that are colder, caused by the magnetic field lines. And in the next slide, you see how the magnetic field lines are coming directly out of those spots. So sunspots are regions that are cooler than the other parts of the sun, significantly cooler. You see that the sunspots are about 4,000 K, while the average temperature at the surface of the sun is 5,800. So it's significantly cooler. Now, connecting those sunspots, and you see the sunspots here, are lines of magnetic field. So these are magnetic field lines here shown in purple. The electrons follow these magnetic field lines. They spiral along, okay, and they travel. And that's what they cause. They call prominences. You see here beautiful prominences. Those are electrons traveling through the magnetic field lines, so you can directly observe the magnetic field lines. The electrons are not going like this, they are spiraling around each magnetic field line and connecting the sunspots. Here you also see the convection zones. That's why you see the granulation that we saw in the figure before. When the gas is going up, you see it brighter because it's the hotter gas coming from the closer to the inner parts of the sun, and then when it's sinking back in, it's colder. So if I go back for a minute here in the granulation, you see those little grains It's brighter, hotter in the center, and it's surrounded by a region that it's colder. That's the cold gas sinking back in. So the hot gas rises, and it gets colder when it comes up in the surface, and then it sinks again, and it keeps doing that motion. So sunspots, prominences, and one more, it's a solar flare. So a solar flare is when there is extra magnetic activity, there is extra strong magnetic activity, and they don't close the loop like that. It's just really a flare into space. So electrons are flowing into space. Okay. So these three kinds of activities, and they are cyclical. So in here I have a plot that shows in the x-axis we have time in years, so I don't know if you can read, but the leftmost is 1900 and the rightmost is 2000. So in summary, what you see is that the number of sunspots rises and falls, and rises and falls, and rises and falls in periods of about 11 years apart, all right? So these are two representations. This is the percentage of sunspots, and this is the number of sunspots as a function of latitude. So you have more sunspots at lower latitudes than at high latitudes. This 11-year cycle brings us back to what we started this little video talking about. The fact that all of this solar weather has to do with magnetic fields and the differential rotation of the sun. So if you go back to the first figure and remember that if you start with the sun with the magnetic fields lines all aligned beautifully, because of the differential rotation, they will start to get entangled and more entangled. And then eventually the magnetic field lines get so messed up that they rearrange themselves and go back to this initial configuration. This is a highly symmetric configuration. In here you don't have much weather at all. It's very calm. So you don't have many sunspots, you don't have many sun flares, you don't have prominences, you don't have any of that. That's boring sun. As the line starts to be more and more entangled, you start to get more and more weather of all kinds. They come together because they all due to the same reason. Magnetic field lines, magnetic field, and differential rotation of the sun. I hope this helps. I'll see you next time.